More in depth here. All right, so let's get started here. We're going to find the inverse function of this. So we're looking for the function that undoes this. So here's our f of x. The notation we're going to use is this. To do the inverse, it is f to the negative 1 of x. This means the inverse function of that function. So be careful. It does not mean this. It's not like 1 over. Some people say, oh, isn't that 1 over the f of x? That's not true. That's actually a multiplicative inverse. If you're trying to multiply by something, we're not. Whoa, that was a big eraser. Did you see that? Holy cow, let's tone that down. All right. There it is. So we got this going on. So this is the inverse function. It's like the Republican canceling out the Democrat when they vote. How am I going to undo this? So really, maybe you've done this before, maybe not, but all you do is this is just like saying y equals. Remember this f of x if you prefer the y. In this case, I think the y is friendlier to work with because what are we going to do? The rule is switch x and y and solve for y. So I'm going to switch these variables. So I'm really saying, oh yeah, that's x equals y plus 2. All of it cubed like this, and now I'm going to solve this bad boy for y. So let's get y by itself. So I'm going to subtract 3 from both sides and say, oh yeah, that's x minus 3. And I've got this whole quantity, not squared, cubed here. So how do I undo that? What is the what undoes a cube? Well, this is going to be the cube root. So that's this opposite right there. Boom. I'm going to take the cube root of both sides. So when I do that, I'm looking at the cube root of x minus 3 equals what? Well, those canceled each other out, so I'm left with y plus 2. And then the final one is what? I'm going to subtract 2 from both sides. So it looks like my final answer over here will be the cube root of x minus 3, that's all underneath the root sign, minus that 2 that's outside of it, equals this. So there is my inverse function. The inverse function of this bad boy is f to the negative 1 of, let's write all that out. The cube root, that's a worse looking 3. There we oh my goodness, what happened? Let's try that again. The cube root of x minus 3, and then we're going to subtract the 2. So what I want to do is I want to take a look at what happens when I graph this. So to find the inverse, you switch x and y, solve for y. So I want to graph it. I already graphed for you the original function. So shift it left 2 up 3, just like 4.1. Let's graph this bad boy. So maybe you don't know what a cube root looks like. That's okay. I mean, maybe we get the general shape. I can plot these points, and I'm going to kind of show you what happens here. So I think of the cube. This is like our h and k. So what is this point? This point is negative 2, 3. What's going to happen here is we're going to have some symmetry when we talk inverse functions. And it's, in the last one we did symmetry about the x-axis or the y-axis or something like that. We are actually going to do symmetry around this line right here. So it's symmetric around this line. What is this line? This line is y equals x. The most basic, like parent function thing possible. Y equals x. So up 1 over 1. So it's symmetric around that. So how will this look? Well, if I'm going to draw this, what happens to this point? Well, if I fold it around this, it's symmetric around this line. This point is it's like how far is it from this line on this side over here. So what is this point when it comes over here? Negative 2, 3 is actually going to turn into 3, negative 2. Isn't that pretty wild right there? So I want to plot some points right here. In my function, if I have the point negative 2, 3, if I plug that in here, a negative 2 makes 3. What's that in my inverse function? Well, you can plug it in. What's going to make negative 2? Well, if you put 3 in here, 3 minus 3 is 0. Cube root of 0, 0 is minus 2. So you can plug and chug some points, but I'm going to pick some points that are very friendly. So check that out. That's interesting. What else happens? Well, this point right here is negative 1, 4. And what's going to happen to that? That's going to turn into 4, negative 1. Interesting. Look at this. This is so exciting. And here's a point right here. This is negative 3, 2. And what do you think it is over here? It's going to be 2, negative 3. So I've got something like this going on. Can I find another place where it hits friendly? It looks like it hits friendly down here, doesn't it? What is that? Negative 4, negative 5. And I know it's going to be negative 5, negative 4. So what's happening here between two tables? It's switching, right? Well, that makes sense. I switched x and y, so I'm switching x and y in my tables. So when I go to graph this function, it looks like it's going to be, did I plot that point? Negative 5, 4. Sorry, I missed a point. Negative 5, negative 4 will be on this side. So what's going to happen? Well, they're both on the line right here, so it's going to hit that. So it looks like it's going to do something like this. It's going to be coming in, and it's going to come through this, and it's going to do something like that. Pretty cool, huh? So we've got that symmetric. If you folded the red line, it's going to fold over and look something like this. So we kind of graphed, that is the inverse function right there. Excellent. So what do we got from this? Switch your x and y's in the table because we switched x and y's up here. So we're looking at We've got symmetric about y equals x. That's our rule for graphing inverses. Awesome, moving on. All right, here we go. Let's go for our next function here. And we're going to find the inverse of this and graph them and then talk domain and range because this is a pretty cool problem here. So let's go back to graphing this. Can we graph this function? Sure. Remember, we've got a We've got a horizontal shift right 3, down 2, and then we've got the stretch. Remember 4.1? We're kind of wrapping up the chapter. Might as well review some of this stuff. So, our normal square root function looks like this. This is our normal square root. So we have to flip it vertically, so around y equals x, boom, flip it, stretch it, then move it. So let's do the flip stretch. If I flip it, it's going to go down and it's going to double. So these points should double. So there's the flip and stretch. So 1 went to 2, 2 went to 4. Oh, I missed it. So there's going to be the flip stretch. So I took these points and see how much bigger. So I went ahead and took the regular, I flipped it, stretched it. So remember, you got to do that first. Stop right there. Stretch, reflect. Now translate. And maybe I can pick that bad boy up. Can I just move him? I'm going to move him. Yes, look at that. That's awesome. Move him right 3, down 1, 2. So there's my function right there that I'm looking at. Something like that. So it's a square root function. I kind of went off the screen here, so we're going to make that a big arrow like that. Goes something like that. So I took the parent function, moved him over. Pretty cool. So I know that it's going to be symmetric about y equals x, but let's solve it and graph it just to kind of make sure we're doing it right. So again, I'm going to do this in one step. This is like y equals, we're going to switch x and y. So I'm going to really say y equals is really x equals, and then I'm going to change my x into a y. So we're going to switch x and y, solve for it. So this one gets a little crazy here, but nothing we can't handle. Add 2 to both sides. So we got x plus 2 equals negative 2y minus 3. And what are we going to do? This solve for y, so I need to get rid of this divide by negative 2. So we're going to divide by negative 2. That's going to cancel out. If you want to break this into 2 fractions, you can. Or leave. I'm going to leave it for now if that's cool. And then I've got this square root of y minus 3. So how do I undo that? Well, what do you got to do to get rid of square root? You got to square both sides. So really, I'm looking at this thing right here. That's pretty cool because that's going to be y minus 3 equals just all of that mess. And you know what? Now I am going to split this up. That's like saying negative 1/2 x. And then what is... I'm not going to flip it up. Why do I'm indecision. Okay, so I'm just going to bring this bad boy down. I got x plus 2 over negative 2. Like this. And then the final step is what? You're going to add 3 to both sides. So add the 3. Add the 3. So I'm going to rewrite it over here if that's okay. So my inverse function turns out to be what? Y equals is the same thing, but it's my inverse. This whole crazy parentheses, x plus 2 over negative 2 squared plus 3. So there's my inverse function. So these two inverses of it. Let's graph this. Can we graph that bad boy? Yes, we can. Do not freak out. We just got to rewrite these parentheses. If we rewrite the parentheses a little bit, you're in business. So this is both being divided by negative 2. So I'm going to factor out that negative 1/2. And what is left? So I took it out of there. I'm left with what? This is going to be what? If I took out the 1/2, it should be x plus 2 squared plus 3. So I'm just rewriting it, and the only reason I did that is why, because now I can graph this. And you can double check it to make sure when you distribute, make sure it's okay there, the same thing. Because I can graph this thing now. So this is a parabola, and we're going to flip it, stretch it, and then translate it. So here's a normal parabola. There's the parent function. Boom, I got my parabola. And now I'm going to flip it, but it's a horizontal. It's in the parentheses. Everything's parentheses horizontal. What happens if you flip this horizontally? Really nothing. It just comes back to itself. But I am going to make it fatter. It's going to stretch out. It's going to be a horizontal stretch of 2. Remember, it's opposite of what you think. So here's my stretched out parabola. Something like this. Pretty cool. Now I'm going to translate it. So let's get rid of my parent function. And I'm hoping I can just pick up my original one and move him. Can I pick this guy up? I'm going to shift it what? Left 2. Yes. Up 1, 2, 3. And there he is right there. So kind of crazy, but that's my graph. Are these symmetric? Well, it's looking pretty weird, isn't it? I'm not seeing the symmetry so much. I mean, it's crazy, but does it reflect? Did I do something wrong here? No, I'm actually pretty good here. It's just weird. Remember, this point right here is negative 2, 3. So this is 3, negative 2. That matches up. Another point looks like it crosses at, here's another point for me, 4, -4, so that becomes -4, 4, and it hits right there. So I got extra pieces though. What is my extra piece? It's this whole chunk over here. So if I erase that chunk, this actually works. So like if this is gone, aha, there is the symmetry. And that's actually what's happening here. When I look at this thing, it is now symmetric. What happens is you have to limit your domain. So always something crazy with your domain. So if I go back to my original function, what was the domain of my original function? So can we see back into this? Let's go back to domain. Remember, set the bottom of the square root. It's got to be what? Positive. So x minus 3 has got to be greater than or equal to 0. So your domain's got to be bigger than 3. So it's allowed to be 3. It's got to be anything bigger than 3. What's the range of that? Well, let's look at the graph. Here's the graph of my original function. This is my f of x right here. So yeah, everything's bigger than 3. What is your range? Well, everything is less than 2. So your range is from -2 to -infinity. Everything below this. What happens this on my new inverse function over here? So to make it the same, to make it reflect, what is my domain? Well, it looks like it is from what? -2 on over to -infinity. And then what is the range of this? How high does it go? It goes from 3 to infinity. Holy cow, check that out. What just happened there? This is huge. The domain turned into the range in the inverse function, and the range turned into the domain. And does that make sense? Sure. This is the x's, this is the y values. This is just them flip-flop. So we're flip-flopping x and y. So huge, huge thing to know. The domain and range swap from, boom, from the function to the inverse. Great problem. I loved it. I think it's going to go a little faster now. So how do I know? Does everything have an inverse? Well, no, they don't. We can kind of trick it to make it, but they don't have inverses. So if I was just going to draw this and say, hey, I can draw one that, I'm going to just draw in my y equals x, and I'm going to say, yeah, this has an inverse, no problem. Whoa, what was that? So it has an inverse, no problem. I'll draw it so it's symmetric. So I'll get in here and say, oh yeah, it's going to go something like this and something like this. But is this blue thing a function? This would look like the inverse. I mean, according to our rules, they're now symmetric. They're symmetric at y equals x. But does this pass the vertical line test? If I drew a vertical line here, what's going to happen? No, it's not going to pass it. So if you look at y equals x squared, it technically doesn't have an inverse. And that kind of makes sense. If I take the square root, if I undo x squared, what are my possible answers? Well, when you do that, it is going to be plus or minus the square root of x. If I go ahead and switch it and solve it and all that, well, this is y plus square root of x. This is y equals a negative. So this is two different functions that do it, but that is not one function. So no, this does not as is have a function. We could go ahead and definitely restrict the domain. We could say, yeah, I only want to deal with the positive. So I could do something like this. And then get rid of all, I can't erase that. Get out of here. Sorry, I can't erase that, it's permanent. But I can cover it up and say, no, it's not there. So we can do restricted domains, but as a general rule, this is a no. And how do you really know? How do you know it's a no? A lot of no's right there. This does not have a function. Well, it's going to be the opposite. Instead of a vertical line test to see if it's a function, we are going to do this. Horizontal line test. So when I draw this line, it's only allowed to touch at one point. So now for inverses, to check for an inverse, you are looking for the horizontal line test. Should I write that out? It's going to take me forever, and my handwriting is awesome. Horizontal line, boom, that's not bad. Test. I'm going to need that space later, though. I'm going to slide it all over here. Should I make it bigger? Boom, horizontal line test. So I'm going to check it. So if I give you this function right here, this is a crazy function. Can you tell me by looking at the graph, does it have an inverse? Well, just slide this up and down. Right here, it passes the horizontal line test to win. Boom. It touches 3 times, and it's still passing. If at any point it fails, it touches more than one point, it fails. So again, I gave you a double whammy here. This is also a no. That does not pass. How about if I just give you points from this? So what is causing this? Well, remember before we didn't like to, for a function, we didn't like to repeat our x's. Now we don't like to repeat our y's. So if we repeat the y value, like the y value here is 2, 2, and 2 is the y value. That's a problem. Did my y values repeat here? Yes, I've got 2 different things making 7. That's not a function. So a lot of times we look at mappings, which is just like you get to draw this little bubble and put your domain in. Here are your x's. So here's my domain. And I'm going to map this on to my range. So here's my domain. Here's my range. And what happens when I do this? So I've got my range 5, 7, and -5. So there's less there. And I start mapping it. -2 makes 5. Boom. 0 makes 7. 2 makes -5. But what happens here? 5 also makes 7. When you got two things pointing at them, it's not going to pass the horizontal line test. So I put no. That's an easy page. Everybody's no. So what is it going to take to make to have an inverse without restricting the domain or doing something tricky? What do I got to do? Well, it's got to be a one-to-one function. What does that mean? It passes both a vertical line test and a horizontal line test. It does both. So when you do a mapping on these, and you get crazy, like sometimes I like to make these look like amoebas or something, or maybe like more like, I don't know, like a peanut, whatever you want to draw it. But when you put these numbers in here, and again, these numbers don't matter. And let's say this is my domain. What's going to happen in my range? 0. Let's say something like that. For one-to-one mapping, it means every x is going to make one y. So I can't have, boom, he makes two different things. Everything's going to be covered like this. Maybe it's something like this. This is a one-to-one mapping. It means each thing in the domain makes its own unique thing in the range. We don't have any double arrows coming out of here or pointing over here. So graphically, what's a one-to-one function look like? Well, it's crazy. To pass a horizontal line test and a vertical line test, what do you have to do? You got to keep moving up. You got to keep going. Whoa, you cannot stop increasing. So these are always increasing functions. If you are one-to-one, the only way to do that is to keep moving up. This passes a horizontal line test and a vertical line test. It's going to have an inverse. Awesome. Or what could you do? You could just keep moving down. And be careful, you can't even go constant. Like that's got to be continuously moving down. You're an always decreasing function. So if you run into one-to-one function, it really just means always increasing, always decreasing. Don't flip out on the vocab. Jot that down. Have that. Holy cow, I feel like I'm talking fast and I'm talking a lot. Let's just, 2 more slides. Let's do this. The proof. How do I prove these two are inverses? So somebody did this and said, hey, are these two inverses? Don't freak out. We're not doing 2-column proofs. I heard somebody groan. Even though it's a video, I heard somebody groan when they saw proof. Don't sweat it. Here's what we're looking at. To prove it, if they're undoing each other, like a square does a square root, we're going to say the f of g of x must cancel each other out and leave you with x. If this was 2, it would leave you with 2. But you also have to show that, if you plug that, they both have to cancel each other out. So a square cancels a square root cancels a square. So really the formal definition is this bad boy over here. That's what I want you to jot down, is this. You need to do both of these. So I picked out a doozy here because I was just feeling like, let's do some hard ones if we're going to do it, Let's bring the pain here a little bit. So let's do it. I want to do the f of g of x. So let's start with the f of g of x. So I'm going to slide that over here. Then we'll come over here and show that these both equal x, and we'll be good to go. All right, so the f of g of x, so I'm going to take my f, and I'm going to plug g into the x, which is this. So I'm going to look at, this is going to be 2 over x minus 3 plus 3. So I replaced x with that. You can put the brackets in there, but they're not doing anything. They're not multiplying, so you're okay. And what's cool here right off the bat, these cancel, don't they? Boom, so that's good. So I'm looking at 2 over x. So this is a complex fraction. Remember fractions like 1/3 divided by 2/5? Remember what you would do? You would flip that second fraction and multiply. Quick flashback there. Same thing here. This is 2 divided by 2 over x. So what are you going to do? You're going to say 2 over 1 is being divided by 2 over x, which that really means 2 over 1 is times x over 2. So flip that bottom fraction and multiply. What happens here? I've got 2x over 2, which cancels. Look at that. It equals x. That makes me happy. Woo! So that's a good sign. But sometimes it works one way. It's got to work both ways. So we got to come over here. Nice. And do it in this one. So I'm going to plug f into g in this case. So I'm going to write, 2 over, oh my goodness, this x is not very friendly though. The whole function goes here, minus 3. So I know what it equals. I mean, a lot of people are just like, hey, it equals x, Mr. Bruss. But you got to actually show it. So same thing here. This is my bottom fraction, 2 over x plus 3. So I'm actually going to say 2 times, flip that over. It's going to be x plus 3 over 2. So if you're dividing by this whole thing right here, it's the same as multiplying when you flip it over. And what's nice about that, there's my minus 3 over here, is these cancel. That's sweet. And I'm left with x plus 3 minus, hey, that wasn't too bad. Not too bad. And look, it equals x. So if you're okay with fractions, and Mr. Sullivan's going to do a lot more of that in Chapter 6, And that is a nice looking smiley face right there. We proved it. They both equal that. You're good to go. Here we go. Let's bring the pain. My favorite part of the video, bringing the pain. So this looks great. No problem. I just want to find the inverse of this bad boy. So I'm going to switch my x and y like I normally do. So I'm going to switch. Here we go. X and y. So this is going to turn into what? 2y minus 3 over y plus 4. I don't see much pain here, Mr. Brust. Just wait for it. Wait for it. So how do I get y by itself? Well, it's kind of weird because I got y's in tops and bottom. I definitely don't like y in the bottom of the fraction, so I'm going to multiply both sides by y plus 4. So really, we don't like the y in the bottom. Whatever you do one side, you get 2 there. So these cancel, so I'm in good shape here. And I'm going to go ahead and distribute this. Let's distribute this out, and what do I get? Well, I'm going to get xy plus 4x. And what does that equal? That canceled out. That's going to equal 2y minus 3. Now this is where it gets a little bit weird. Here's a little bit of the pain. I'm trying to get y by itself, but I have y on both sides. So I need to get all my y's grouped together. So anything with a y, I'm going to bring over here to the left side. So I'm going to subtract 2y over here. So I'm going to get xy minus 2y plus 4x equals negative 3. Anything that does not have a y needs to go. So I only want y's on the left, so I'm going to subtract 4x from both sides. Do not want anything that doesn't have a y over here. So I've got xy minus 2y equals what? Negative 3 minus 4x? Something like this. This is the weird part. So I'm going to bring the weird part up here so we have plenty of room so you can see this. Do I got it? Where'd you go? Got it? Where? There? No? Here? There it is. All right. Let's bring it just up here so you can see it. So I'm going to bring this weird part up here. And what's so weird about this? Well, I'm going to factor out what they have in common. They both have a y in common, so I'm going to undistribute that y. So when you undistribute it, you're looking at what's left. X minus 2 equals negative 3 minus 4x. And then what do I do here to get y by itself? Yes, you just divide by x minus 2. So it's not too bad. That's the part that's kind of unintuitive, pulling out the greatest common factor of y. But once you do that, those cancel, and I'm left with y equals negative 3 minus 4x all over x minus 2. Or you could have said negative 4x minus 3. There it is right there. Awesome. Excellent. That's the end of 4.4, the end of the chapter. It's been a good chapter. I hope you do well on the master check and on the test. I've got a pretty good clip lined up for you on inverses. I think it's pretty awesome. This is a woman's